So in Gaussian elimination, we start with our linear system of equations. We write it as AX equals B, but instead of writing AX equals B, we write the augmented matrix, in which we simply write the coefficients on the left and then the independent coefficients on the right. Okay, so we start with this augmented matrix, which we could call it a line B, and we do Gaussian elimination, which is a series of operations which are called Gaussian steps. And I'm not going to tell you what these Gaussian steps are yet, okay? I will do that later. But basically, very, very quickly, it's equivalent to when you add and subtract equations one with the other, okay? But the point of this is that by doing those operations on the rows of this augmented matrix, we arrive at another augmented matrix, which we could call U line C. But the aim of the Gaussian steps is that this matrix U is in row echelon form. And why do we want to arrive at row echelon form? I will explain later, but basically once it's in row echelon form, then we can solve the system very easily. But in this video I will talk about what row echelon form is. So this is an example of a matrix that is in row echelon form. So what is all these asterisks and ABC and all that? What is all this? Okay, don't worry. So this is an augmented matrix. So you see you have a matrix on the left, which are the coefficients, and then you have a vector on the right, which are the independent coefficients. All of these asterisks are simply a way for me to say a number goes here, and it can be anything. It can be a positive number, negative number, it can be 0, it can be a complex number, whatever, yeah? But it's a number, any number. The point is that when I write 0, then that is a 0, okay? It cannot be anything else, it has to be a 0. These numbers that I highlight, A, B, C, D, and E, these are non-zero numbers, okay? And they are called the pivots. So the pivot, the way you identify a pivot is, for example, so each row of this matrix has a pivot. So how do you find the pivot? Okay, let's take the third row. The third row. So this third row starts with 3 zeros, then it has a non-zero number, and then it has something else. I don't know what it is. It might be 0, it might be non-zero, whatever. But the first non-zero number of this row is called the pivot, okay? So since here C is not a 0, because I said that these A, B, C, D, E are non-zero numbers, so then this number is the pivot. And I use this hexagon to say that this is the pivot, yeah? So similarly, let's choose the first row. What is the pivot in the first row? Well, the first row starts with a number that is not 0, so the pivot is that first number, yeah? So what is this fifth row? Which is the pivot in the fifth row? Well, it starts with 0, 0, 0, 0, 0, and then it has a number that is not 0. So that is the pivot, okay? Okay, and this matrix that has all these zeros here on the bottom left side, is in row echelon form. So let me rigorously define what row echelon form means. A matrix is in row echelon form if two conditions only, okay? First condition, all rows that are all zeros are at the bottom. That is the first condition, okay? So in this case, we have one row in which all of the coefficients are 0, and that row is at the bottom. Good. So we fulfill the first condition. That's the easy condition. The second condition is a bit more complicated. The first non-zero number of each row which is called the pivot, as I told you, is always to the right of the pivots of the rows above. So let's think about this. So let's look at all the pivots, which I marked with hexagons here. So this first pivot, is it to the right of all the pivots of the rows above? Well, there are no pivots in the rows above, so yes. This pivot B, is it to the right of all the pivots from the rows above? Well, it's to the right of this pivot A, right? It's to the right. It's in a column that is to the right of the column where A is. So then yes, the answer is yes. C, third pivot. Is it to the right of B? Yes, it is. D, is it to the right of C? Yes, it is. E, is it to the right of D? Yes, it is. Okay? So this matrix fulfills this second condition. When these two conditions are fulfilled, what happens is that there is always this block of zeros on the lower left corner of the matrix. Okay? This is a result of the two conditions. Yeah. So the definition of pivot, together with the fact that pivots have to be to the right of the previous one, it means that you are always leaving zeros on the left. Okay. So let's write that. Therefore, every pivot has zeros to the left and to the bottom of it. Okay. So in particular, every single pivot always has zeros below. Okay. Something that confuses students a little bit is they think that something is a pivot if it has zeros below. But that's not the definition of pivot. Remember that the definition of pivot is that it's the first non-zero number of each row. So for example, this number here, imagine this number here is not zero. Is this a pivot? Well, it's not a pivot. Even though all of these are zeros below, it's not a pivot because the first non-zero number of that row is A, is that first element. Yeah. So this is not a pivot. Yeah. Okay. So this matrix is in row echelon form because it fulfills these two conditions. And therefore it has this special look in which all these zeros are bunched up in the lower left corner. So next, let's talk about columns that have a pivot and columns that don't have a pivot and the properties of these columns.